Bonjour à tous.
So,
Je vous propose
good
qu'on commence
afternoon. Let's
webinaire.
start our
En attendant qu'il
webinar.
y ait
Just
encore
a
des gens
couple of
qui se
words of
connectent.
introduction, then I will give the
Quelques petits
floor
mots
to the
d'introduction et puis ensuite laisser
students,
la
the
parole aux
master
étudiants du
students.
master EWS.
This
Donc ce webinaire,
webinar
il est
is organized in the
organisé
framework of the
dans le cadre
Water
de la
Week
semaine de l'eau H2O Lyon.
H2O Lyon,
Donc
which is
H2O Lyon,
the
c'est une
H2O
école
Lyon is a
universitaire
research
de recherche
institution which
qui
comprises
regroupe à
all
Lyon
masters dealing
tous
with
les
water
masters
science and
sur
all
les sciences de l'eau
research
et les
laboratories working on
laboratoires de
soft
recherche qui
water
travaillent sur l'eau
or
douce de
fresh
manière
water,
générale,
basically, as
en
globally.
essayant de
So we
porter
want to
et
promote
de favoriser
interdisciplinarity, link
l'interdisciplinarité,
up with
le
the
lien avec
players in
les
the
acteurs des
region
territoires,
zones, and of course,
également le lien
international
avec
links as well.
l'international,
And we want to
et puis
combine training and
d'associer la
research. And
formation à
within
la
this
recherche.
framework,
Et donc dans ce cadre-là, on
we
porte
have a master, which is
un
Integrated
master qui s'appelle
Watershed
Integrated
Sciences,
Watershed
and
Sciences.
the
Et dans le
students
cadre de ce master, les
are
étudiants
able
ont
to
pour projet durant
organize
l'année d'organiser
webinars.
des
This
webinaires.
year, the
Donc cette
thematic
année,
is the
leur
use of
thématique a
AI
été sur
for water
l'utilisation de
sciences.
l'IA
And so there will be
pour
two
les sciences de
webinars.
l'eau.
Then I
Et
will
donc ils
give
vont
them the
proposer deux
floor.
webinaires.
Kevin
Je vais ensuite
Vical
leur
will
laisser la
be the
parole. Donc c'est
facilitator,
Kevin Vical
but
qui
within the
va
group
faire
of students,
l'animation. Mais dans ce
there are
groupe
also four
d'étudiants,
other
il y a
students.
également
They
4
might
autres
introduce
étudiants
themselves at the
qui
end.
peut-être qui se
Mathis,
présenteront à
Valpa,
la fin.
Ricardo, and
Donc
Sampada.
Mathis, Pourva, Ricardo
So with no
et
further ado,
Sampada.
I give the floor to
Et voilà, je
Kevin
vais
for
passer
the
la
rest of
parole
the
du coup
webinar.
à Kevin pour la
Thank you,
suite du
Claire.
webinaire.
Please, sorry.
Merci
So
Claire-Lise.
today we
Alors du
prepared the
coup,
webinar on the
aujourd'hui,
topic
on a
of
préparé un webinaire sur le thème de
AI
l'intelligence
and the
artificielle
remote sensing
et
to
le
to
remote sensing
identify or
pour monitorer
work on
la
rivers.
rivière.
When
Pour
it
ce qui
comes
est
to the
des
speakers
internationaux
we will
présents
listen to
aujourd'hui, donc on
today,
a Simone
Simone
Bizzi, qui est
Bizzi, who is an associate
professeur
professor at
à
the
l'Université de
University of
Padua
Padova in
et qui
Italy,
a
who
publié
published
de manière
quite
extensive sur
significantly
ce
on
qui
the
est
world of
du remote
in the
sensing
domain of
et
remote sensing and
de la
river
géomorphologie fluviale
geomorphology.
notamment.
And then
Et puis on
two
a deux
PhD
candidats
students,
en doctorat,
Isabelle Brichetto
Brichetto et Léo
and
Helling,
Leo Elling, who
qui
are
sont aussi
also
en
PhD
doctorat
student
sur
on
ce
the
sujet-là.
same with the same domain.
Comme l'a dit
And as
Claire-Lise,
clearly said, I will be
la
the
présentation
facilitator
commence
of the
une heure,
webinar,
mais
but
il y
we
a toute une équipe
are there is a
d'étudiants
whole team
derrière,
of
donc
students behind me,
les autres
so
se présenteront à
the
la suite
others
du
might
webinaire.
introduce
Val, Ricardo, Mathis
themselves
et
at the
Sampada
end
qui
of the
vont aider à la
webinar.
préparation de ce
They
webinaire.
will introduce themselves
Voilà, je vais
because they help
laisser
me. So with no further
peut-être
ado, I will
Isabelle et Léo se
let
présenter à leur
Leo
tour et
and
puis
Isabelle introduce
commencer cette
themselves and
partie
they can
présentation.
start delivering their presentation.
Okay, so thanks. And so how, as Kevin was saying, I'm a PhD student in environmental and land engineering here at the University of Politecnico di Torino, located in Italy. In particular, as you will see after, I'm focusing my research on non-perennial rivers. So it's a particular field of surface water dynamics, but we will enter in this theme later on. For now, firstly, I will present together with Leo an overview on water mapping across the globe. That is the first part of the webinar on AI and remote sensing at the river service. So let's start thinking about water from a very general point of view. All life on water depends all life on Earth depends on water for existence. But how much water is present in our planet? Well, actually, the 70% of the planet's surface is covered by water. The three blue spheres represent relative volumes of Earth water in comparison to the size of the globe. Water occupies a very thin and superficial layer of our planet, and this explains such differences in volumes. So, looking at the first bubble, the largest one, it represents all water on Earth, including the salty and fresh water, and in every physical state. As you can imagine, the oceans are the largest share of this bubble, and just the remaining 2.5% of the total water is fresh water. and the majority of it is locked and blocked in glacier and ice caps. In fact, if we want to consider just the liquid fresh water, we have to look at the second spheres, blue spheres. That is the resources that we use as animals, vegetation, and humans for our everyday needs on Earth. Considering then just the surface liquid water, we end up with the third very tiny bubbles that represents just the 0.007% of the first one. Hence, surface water is essential for drinking ecosystems, but also biodiversity, human activities like agriculture, industry, manufacturing, and energy production. So we heavily rely on a very rare commodity. And for this, it's quite understandable why it is important to study such distribution of water across the Earth. And actually, the answer is to meet global human needs while preserving water quality and aquatic ecosystem. But is water enough on Earth or not? Actually, yes, or almost, because although it is theoretically enough, there are large geographical and seasonal differences in its availability. In fact, the quota we previously seen represents a static image of the distribution over the different water compartments. But as you can expect, water is highly dynamic. It constantly changes physical states, but also shape, position, drawing the beautiful schema of water cycle. The water cycle is the continuous and naturally occurring movement of water through atmosphere, biosphere, and geosphere, through the climate system from its solid, liquid, and gaseous form. The moving engine of all this cycle is the solar heat that induces the water evaporation and transpiration from the surface to the atmospheres. Once water vapor condenses and accumulates in clouds that are then shifted by winds and atmospheric currents, water precipitates in the form of rain, fogs, snow, or hail. Once back to the surface, liquid water can infiltrate the soil and recharge groundwater or flow across its surface, arriving through runoff to rivers, streams, basins, and once again, oceans. This is a mapping of water fluxes, but how does the word mapping mean? While referring to freshwater, mapping is the process of identifying, measuring, and monitoring the location, extent, and characteristics of water bodies. It is very important for understanding the water resource condition, but also the related issues. Which data and which tools we can now use to map freshwater? Actually, the answer is a combination of remote sensing and GIS technology, but also of ground-based sensors and surveys that are used to track water, and hydrological modeling that is instead used to reproduce water dynamics. Concerning data from satellites that describes freshwater, I present here the GRACE mission of NASA. Launched in 2002, its goal is firstly to map how the distribution of fresh water around the planet is changing. These satellites indirectly measure the variation of Earth gravity field caused by the movement of water masses. This video illustrates the liquid water thickness measured over time by the missions. The data show that in some region, water supplies are relatively stable with zero anomaly, while other regions experience an increase, the blue areas, or decreases of the freshwater amounts. The causes of this anomaly can be natural, but also anthropic, related to groundwater depletion or irrigation purpose, or linked to climate change. But to our interest and more related to direct Earth observation, while the previous was sort of an indirect satellite observation, it's fair to mention the Landsat mission that firstly observed the surface globally with a high resolution, in particular 30-meter resolution. Thanks to the data of Landsat, Peckel and colleagues quantified the spatial and temporal variability of global surface water over a span of 3 decades. They performed a pixel-based classification. Before these studies, we knew that water moved, but we didn't have a high resolution way to see exactly where it is disappearing or appearing. These images at the left shows the transition between 1984 and 2015 of water presence among the Aral Sea at the top and the Tibetan Plateau at the bottom, distinguishing between permanent, seasonal, and ephemeral water. The work of Pickens and colleagues is a kind of a continuation of this approach. It focuses in particular on interannual dynamics, fixing uncertainties of the classification, and identifying areas with water gain or loss, with also seasonal changes. But now, to discover a bit more on satellites and how they function, I'm passing the floor to Leo, that will continue.
Thanks a lot, Isabelle. So now to understand how satellites or how this data is actually produced from the maps that you have just seen before, and also to give the floor for our next presentations, we will give you a quick introduction on satellites and also how machine learning is improving the mapping of water surface dynamics from satellites. So in this presentation, we will only or mainly talk about passive sensors, data obtained from these sensors, which measure the sun's radiation that is reflected back from the Earth into the orbit, in contrast to active sensors, which emit their own signal and measure the returned energy. So when you look at the electromagnetic spectrum of radiation, you can see that with our own eyes, we can only see a small part of that radiation, actually. And satellites enable us to measure a greater part of the radiation, and especially this helps us to better map water. To get a better understanding of this, you need to understand that different surface cover types on Earth reflect differently the radiation. And for example, if you look here at concrete, that reflects or has a high reflectance value over the whole range of wavelength that we can measure with satellites. Whereas, for example, bare soil here in orange has high reflectance values in the longer wavelength spectrum, whereas in the shorter wavelength range, the reflectance drastically reduces. And for water here in brown and dashed light blue, you can see that it mostly doesn't reflect a lot of radiation. Only in the short wavelength, the reflectance values are a little bit higher. And with optical satellites, we can measure the strength of this reflectance. So what you would normally have is that a satellite measures within different ranges of this electromagnetic spectrum. It measures the strength of reflectance. Normally, you would have at least the blue, green, and red band, but often you have the near-infrared band and even more bands distributed along this wavelength, along the longer wavelength as well. And by combining these, you can create different maps or different images. The classical one is the RGB combination. So to create a true color composite, combining the blue, green, and red band. And here we have an example of this from Sentinel-2 imagery from the Rhône Delta in France, where we, with our own eyes, we can already identify the river and the other surface water surfaces. But automatically extracting this information is more complicated. And this is where we can get use of the other bands from the satellite imagery. For example, if we look at the near-infrared band, you see that other surface cover types have rather high reflectance values in the near-infrared band, whereas water has very low reflectance there. And for the green band, you can see water has a higher reflectance, still very low compared to the others. So combining these two bands helps us to create a contrast between the water and non-water surfaces. You can see here the example of the same image, just combining the near-infrared and the green band. And you see that it creates an index from -1 to 1. And this is often done. That can be done for vegetation, for bare soil. There are different indexes, different combinations of these bands, where you can increase the contrast between different surface cover types to be able to automatically extract the information about the water surface from the imagery. And what you would normally do is to apply a threshold to say everything above 0 is water. But there are these artifacts such as clouds that create also low values. And you can see also that, it's not constant for the water surface. So depending on the sediment load, on the vegetation within the water, the values might be lower. So often this thresholding needs to be locally adapted to work well. And this is where machine learning can improve the analysis. But before talking about machine learning, another important aspect is the resolution. Spatial resolution and temporal resolution are two very important aspects because often you have to find a compromise between both of them. So increasing the spatial resolution increases the spatial detail, and you can see here clearly on this image. And increasing the temporal resolution means basically that that the different satellites that are out there, the different satellite systems, they have different recurrence times. So some, they pass each location on Earth every day, and some only every 2 weeks or every month. And then a third aspect of resolution is the spectral resolution. So how much bands do you have? The more bands, the more detail you might have to improve your mapping. So in general, it means that increasing the resolution improves the analysis, but it also requires the handling of more data. So this is where often you need to find a compromise. And machine learning can also help in this aspect. So machine learning, we call it here more machine learning than artificial intelligence, which is a very general term. Machine learning are algorithms that learn patterns and relationships from data to make automatic predictions or classifications from them and also to new data. And here to map water, it can, for example, help us to separate water from non-water pixels, but also identify pixels or better distinguish pixels where there's only a part covered by water and the other part of the pixel is covered by vegetation, for example, or to treat missing observations such as those caused by clouds, where, for example, interpolation can be an option, but also the integration of other sensor data such as radar. And you can also create with machine learning models workflows that are more globally applicable if you train them well on global data sets and under a variety of conditions. And finally, also super resolution, increasing the spatial resolution is also something that is be done and that is still under research. in general, what you need to learn is that normally it works like that you have a model that you here in the middle, for example, a neural network, but can also be a classical machine learning model, such as a random forest or a support vector machine. And what can be done, or what is done, is that you train that model with images, with the raw images, and with labels, where you label, for the case of water mapping, which pixels are water and which are not water. So the model learns from that. And when you give it then new data, it automatically predicts which pixels are water in that on that image. So those were the basics about water mapping and remote sensing and machine learning. And now there will come our 3 case studies, or 3 aspects specifically applied to river systems. And in this first presentation, I will talk to you about the lateral river flow variations that we study here at the EVS lab in Lyon. What are lateral river flow variations? Lateral river flow variations are just simply the variations of the water surface extent in rivers caused by the variations of the discharge. And this can look simplified like this, that you have a variation of the water surface within the active channel. But over the long term, these variations cause the moving of the whole river channel, or might cause the moving of the whole river channel. And short-term events such as flooding and inundation, they even sometimes increase as much the river area that it causes flooding of the riparian zones and the floodplain. Of course, these river flow variations are here highly simplified, and they depend a lot on the actual river system. But in general, it can be said that they provide a variety of ecosystem services. They create and maintain habitats for fish, for plants, for macroinvertebrates and birds. They cause the redistribution of sediments and water, not only within the river, but within the whole, maybe within the whole valley floor. And yeah, they also cause the attenuation of flood peaks. So there are a lot of benefits of these. But most rivers, especially in Europe, are highly modified by human activity, causing a reduction of these flow variations. Here you can see an example of a dam, which causes the reduction of the, or a regulation, which causes a more regular flow and a reduction of these flow variations within the channel. But occupation or utilization of the riparian zones and the floodplain for infrastructure and stabilization of the bank also reduces the space in which natural rivers might laterally move. And finally, the construction of dikes and levees disconnects the rivers from, or disconnects the floodplains from the rivers, and prevent the transportation of new sediment and water into the riparian zones, which actually create fertile soils and a lot of other benefits. So both of these benefits and the human impact, it is important to map them. But until now, there have not been a lot of studies which specifically try to map these, because we simply need a lot of data for that. We need imagery or satellite imagery with a high spatial resolution and temporal resolution to be able to really see where is and was water occurring within the river corridor. So in the goal of this study, we aim to develop first the tools to generally map these water occurrence variations, and then translate them into meaningful metrics to be able to map these variations over the river network. And for that, we first turned to Landsat data. However, applied to French rivers, the data is too coarse. Here you can see the example of a data set which is ready, which Isabelle already presented and which is ready to be used. It's by Pekel et al., which informs about the occurrence within a year or multiple years of water. However, the spatial and temporal resolution is not enough in a rather medium to small size river systems in France. So we turned to Sentinel-2 imagery with 10-meter resolution and 3 to 5 days recurrence times, improves the detail. However, there's no ready to be used data set out there. So we thought that dynamic world might be a solution. Dynamic world is a deep learning segmentation neural network developed by Google and is automatically applied to all Sentinel-2 images out there. And it provides probabilistic land cover classifications among these, or for these 9 land cover classes. And among them, there's also a class for water. So we thought that, we could just simply use this data set, but there are no studies out there which checked if the model is actually works well to only map water too. So we undertook an analysis. We evaluated dynamic world to map water from Sentinel-2 imagery, and what we found out under this global study that it actually works well. But it works best if we fine-tune it with the normalized difference water index, so this spectral index that I've just shown you before. And yes, if you have specific questions related to this, I will not go into deep detail here, but don't hesitate to ask later. But this hybrid approach enables us to have a quite efficient and scalable method to map water extent from Sentinel-2 imagery. So then we included this method into a workflow on Google Earth Engine, a cloud computing platform, where we automatically process the whole amount or the whole stack of Sentinel-2 imagery available within 1 year and aggregate that over months and years to have this information of the occurrence of water at a specific point within the river corridor for a specific period. And we applied that to the whole Rhône River basin in France. And compared to the original data that you can see here, our data set highly improves the spatial and temporal detail. So we have a lot more observations, and the 10-meter resolution is 3 times higher than the Landsat data set. And what we are then doing with this raw data is that we mask it with a river corridor, where for each of these segments, we extract metrics and then aggregate them and to be able to map over the whole river corridor the different metrics. And for the case of active channel flow variations, first results look like this. For the year 2021, you can see where rivers were more active and less active within the French Rhône-Mediterranean basin. Rhône basin. You can see mainly here in the southern parts, you have some river reaches which are still dynamic. And when you look at the data, it looks like this. So here the Isère River in the central part, it is super stable throughout the year. Whereas the Durance River in southern France, you can see these variations, and you can see that the channel is not stable over time. For the second aspect of lateral river flow variations, the active channel mobility, so the difference between several years, how the water and active channel move over time. I can present you this example. The result looks pretty similar. So only in this southern region, the river channel really moved between these 10 years of data. And even not only it was basically the water channel, not the river channel, that moved here over time. And the third aspect, the flooding, which is also an important aspect of these flow variations. Here the map looks a little bit different. We only look at the year 2021, and in that year there was a big flood in the Son River in July 2021, and we can actually see from our data these the flooded floodplain of the Son River and some parts of the agricultural fields being flooded. And in the central part of the Rhone River, you can see there were almost no flooded riparian zones. So to conclude, river flow variations drive important ecosystem services, but are often strongly altered by human activities. And mapping them requires satellite imagery with high spatial and temporal resolution. And here we provide, or we present a hybrid approach where we combine deep learning model with the normalized difference water index to enable large-scale mapping of water extent variations from full Sentinel-2 time series. And these data enable new opportunities which we are still discovering to inform about river ecosystem conditions and about the specific aspect of lateral river flow conditions. And future steps include the investigation of the hydrological representativeness of these data sets and further aspects of which metrics we can derive from these data sets. So I think now it's time for questions. And thank you for your attention.
Thank you, Leo, Isabelle. I don't know if I didn't see any question in the chat for you. No question. Okay, Leo. So maybe I do have a question. It has to do with, I wanted to know how eventually these interesting data can be used in practice. Can I put it to assess the condition of lateral connectivity of a river versus what could be expected from the river vis-à-vis what can be expected for the river in that context? Can it be used to quantify, to have lateral connectivity index and possible improvement following restoration projects, for example?
Yes, so I mean, that is the goal to inform about lateral connectivity. Lateral connectivity is an important aspect of in general of the ecosystem condition and processes in rivers, and which is not studied so much because you need this temporal data or this temporal aspect. So here, really, the idea is to create metrics along the river network and then really create these maps to be able to inform about the parts of the river networks where rivers are more dynamic and other parts where they're less dynamic. So it's the end goal is really to inform about this lateral connectivity. But for that, there's a lot of work to be done to treat the data and then also to think about because lateral connectivity can mean a lot of things. And also in the EU biodiversity strategy, it is included in the restoration of in the restoration targets for European river systems. But what they use is a very static analysis. But actually, we think that with this satellite imagery we could inform a lot more about. But these are still like the first steps a little bit how we can use it, because until today it was hard to process these large amounts of data and to have the models that can do that. So we hope that in the future we might be able to develop methods that can then be used to directly inform management and policy about this.
Thank you. A question just been asked in the chat. Finally, are there any tools that are being developed for people who are not necessarily expert in remote sensing or in AI? So you talked about models that already have been trained by the the Sentinel-2 device,
Est-ce que c'est
are
des
these
questions
things that can be used
utilisables
by
par
people
des
who are
personnes
not
qui sont pas
expert,
expertes
or is it
ou est-ce que
still
c'est encore
limited
finalement
to
réservé
experts?
à des experts
Are
parce qu'il
there
y a d'autres
tools which
champs
are simpler
d'utilisation?
to use?
I think there are more and more tools out there. So for satellite imagery, there is the Google Earth Engine platform by Google, where you can relatively simply get, for example, from the dynamic world model, these predictions, land cover predictions, or you could apply by yourself a normalized difference water index. But I think there's also by the European Union the Sentinel Hub or Copernicus platform, where you can directly download these normalized difference water index maps, where you can then separate water from non-water pixels relatively easily. You need to have some geography background maybe to treat geographical data, but it is not as complicated. And often you can directly download the data for the normalized difference water index, for example. You don't need to calculate them this by yourself. So there are some platforms out there. I can send them in the chat here if people are interested.
Merci beaucoup, Léo. Il y a une question du coup qui vient
Another question in line with the question I was about to ask concerning the scale. We've seen that in long river, you talked about 10 meter resolution. Does it apply to smaller water bodies, or is the resolution too coarse to be applied to smaller rivers or water runs?
So the problem is the more you increase the spatial resolution, the more data you have to treat. And there are some satellites which are out there which provide higher resolution data, notably Planet, which is at 2 to 3 meters, or there's even some commercial providers that provide data at 1 meter. But then the issue is really the amount of data that you need to treat. But yeah, there are definitely webs out there, and it depends a little bit if you want to look only at seasonal data, at annual data, or if you really want to also look at these short-term dynamics as we do here. But yeah, of course, definitely resolution is a limit, and these global satellite programs, with them we can mainly analyze large rivers such as the Rhône, Durance, Isère. Yeah, for rivers such as the Drôme River, it already gets complicated with Sentinel-2, for example.
Ok, merci beaucoup. Du coup, on va
So
passer
let's move on
directement
to
à la
Isabelle
question d'Isabelle, qui est une question par
communication.
écrit, on la posera peut-être par la suite pour rester dans le temps.
So Isabelle,
Isabelle,
can you
tu peux
share
partager
your
ta
presentation, please?
présentation. Merci, Léo.
So, thanks. As expected and also announced, we are now passing to my field of research, that is non-perennial rivers. And looking on having an overview on this river system, but also focusing on the challenge they are posing to the scientific community. Okay, so let's start from the definition of non-perennial rivers. Actually, they are river systems characterized by the occurrence of non-flowing periods. This means that together with the normal flowing condition, they experience also the ponding condition, in which water is present but in a discontinuous way across the riverbed, showing ponds or cut portion of low flow channel. But also they experience the dry condition with riverbeds completely dry, so without water. The identification of this free hydrological condition is made and can be made at the ridge scales. The phenomenon of river intermittency is very common and widespread, and it can be caused both by natural causes, so following the water cycle dynamics, but also by human-induced pressures such as water depletion from for drinking purpose or irrigation or whatever. Such river systems are, as you can expect, highly dynamic, with deep variability both in space and time. Now that we have understood a bit what river intermittency is, the question is how to map which portion of a river network experience non-perennial behavior, and how to monitor such evolution in times among the three different hydrological conditions inside the river basins. Actually, the answer, once again, is to rely on environmental data, surveys, but also on gauging stations, so on directly collected in the field data. But if we look at water level measurements, we realize that they are very scarce and cannot properly detect, for example, the difference that exists between the ponding or the dry phases, because actually detecting zero flow wouldn't tell you much information about the hydrological condition occurring in the place in which the gauging station is located. So the other sources is to rely on high-resolution satellite imageries, like the ones that Leo introduced you, that are Landsat, Sentinel, and Planet, that has the highest spatial resolution. And satellites in recent decades transformed our ability to monitor Earth's surface dynamics, as previously shown. So, as challenging task, non-perennial rivers requires innovative technologies and methods that should be integrated in order to provide answers and advance in the research. And in this framework, machine learning perfectly helps in fitting data and retrieving information from this amount. So let's discover a bit more on how machine learning specifically has been used in the non-perennial rivers framework to answer some scientific research questions. So the one we will start from is the questions of what is the global extent of non-perennial rivers. So we have seen that is a common phenomenon, but how spread it is. Actually, starting from multiple types of data, and in particular using environmental predictors in the category of climate, hydrology, land cover, physiography, and geology, Messenger et al. Developed a statistical random forest to produce an estimate of global river intermittency. Actually, random forest is a machine learning model that works by using many aggregates decision trees that are collectively called forest to make a prediction. And so it acts as a flowchart of condition, and it's used to accurately classify or predict outcomes. In this case, the aridity index within the environmental predictor and the hydrological variables demonstrated to be the main predictors of the flow intermittence. And thanks to the correspondence in data learned by the random forest, the model predict that water ceases to flow at least in 50% of the global river network, revealing that river intermittency is a sort of normal phenomenon within rivers. As results, they obtained an intermittency map of 20 million kilometers of rivers and streams across the entire globe, with the probability of ceasing flow at least of 1 day per year. In order to have to continue these studies and to have intra-annual understanding of the phenomenon, Doll et al. Refined a bit the modeling approach. In particular, they estimate the monthly time series of stream flow intermittence at high spatial resolution in Europe. This is because the output and the results of Messenger was a static image resuming the behavior of the river network in the last 40 years. And so the following part of the research was to look more particularly at the monthly dynamics. So not just having an overview, but looking if we are able to extract some time series about the streamflow intermittency behavior. In order to do that, some variables retrieved from the water gap hydrological and global model was downscaled and fed as input in the machine learning models. Actually, the months were classified and predicted in 5 classes basing on the experienced number of non-flowing days. And these here laterally are represented, the output within these 5 classes for a particular location. Following what has been done in the framework of non-perennial rivers, Cavallo et al. Used the satellite observation, finally, to retrieve the daily occurrence of hydrological condition in non-perennial rivers. And they applied this methodology over a specific region of Mediterranean zone. Once again, they coupled the data, like meteorological data, with satellites in order to learn what relation exists within, for example, rainfall data or water level and the condition observed and attribute in a qualitative way via satellites, relying on the emission of Sentinel-2 that has a ground resolution of 10 meters. The random forest ENS allowed to pair the intermittency classification with meteorological predictors, and the output has been daily estimates of river hydrological condition with satellite gaps, considering that they have revisit time of 5 days, but also considering that in case of clouds, we are not able to see what is the condition occurring at the surface. And so using random forest, they fulfilled the gaps within satellites of observations. More recently, and here we pass to the another studies, the question has been no more just understanding how to monitor the condition, has been done as the other was doing, but also how to forecast river droughts. And for predicting stream flow from 1 to 13 weeks on, the approach of Hammond et al. Have been to train and test both a neural network able to learn features while remembering what happened and what has been learned in previous steps. And in particular, they use the long short-term memory neural network. And also they test and use a sub category of decision trees that is called the gradient boosting algorithm that is used specifically for forecasting. The figure you see here at the bottom show the related reliability map of the 2 models. And so how well they predict the possible outcomes. In particular, on the y-axis, you see the percentage of stream flow in the previous years. So below this black line of 20%, we consider the stream flow to be in drought. And while the x-axis tells us how far into the future the model is looking. So as I was saying before, from 1 to 13 weeks on. The results has been implemented in a website that is called the Riverdraugcast, but it's intentionally made for the United States. But here is how it is appearing, and it is completely user-friendly, telling you, basing on the data of gauged location, they consider to build all these forecasting model, what will happen in following weeks, actually. For presenting you a last example, and this is the research I'm working on with my team in Politecnico. Here is the framework on the scientific questions we are trying to answer. That is, how can we automatically monitor hydrological condition basing on satellite observations? Well, for this approach, Sentinel-2 images, as previously shown and demonstrated by other researchers, can actually contains a high amount of information related to the river intermittency dynamics that we can use in order to reconstruct what happens to a specific river reach. For this goal, we are using a convolutional neural network that is an algorithm able to recognize patterns in images and learn relation that exists within pixels. Hence, we are training a convolutional neural network model in order to classify new images derived from the Copernicus mission and classifying them into 4 classes that currently are the flowing, ponding, dry, but also the cloudy classes, as Sentinel is a passive sensors. A similar tool will allow to reconstruct the time series of hydrological condition over time, and thus to have much more information about the frequency and duration of non-flowing periods. In fact, we can retrieve information such as this time series showing how this specific river reach evolve in time, and this is for the last 9 years, but also how was the distribution of non-flowing events durations among these time windows. As final remarks, I state the following points. And first, the fact that river intermittency is a fascinating field of surface water dynamics. And considering their diffusion and ubiquity, we have seen that estimates tell us that half of the global river networks go intermittent. But despite this, these water courses are still overlooked and not that much studied. Hence, remote sensing data, thanks to the missions that are more and more frequent but also affordable, should be coupled with other environmental data and predictions in order to monitor and forecast river intermittency. And finally, the fact that machine learning helps us in combining data, especially if they are of a great amount, but also in the process of upscaling and generalizing approaches. For concluding, the question is what's next? And actually considering all these pieces of Lego together, what's next is a global implementation of technologies for having automatizing actually the procedures related to water mapping. And this was all. Thank you.
Merci beaucoup, Isabelle,
Merci Isabelle pour cette. Thank you, Isabelle, for this presentation, for the very interesting topic. Well, I do have a question. It has to do with the limitations of the use of remote sensing and AI to map intermittent rivers. Is it a solution that works well enough? Do you need to do additional on-site data surveys? Or what are the limitations of such a technique?
Actually, it depends on what is the scope. For example, yes, as also previously stated and pointed out, the physical limits of satellites is the spatial resolution. So we are able to see rivers. Actually, for the approach we are developing, we focus on rivers that are wider than 30 meters in terms of active channel. But since every pixel is 10 meters per 10 meters, we are not able to see littler streams, for example. So it comes naturally that satellite at this stage cannot be used to map all water courses in general. So there are inner limits. But if we want to have actually a guess of what is the river intermittency behavior as observed and not just predicted by models, satellites can still give you a lot of information and a lot of data. So the point is, we know that not all the water courses could be seen, but at least we start from what we are able to see and classify. Regarding instead the limits of using machine learning, users, but also developers have to realize that errors can be produced. So if you forced a model to generalize a lot of data with less validation or not strong error checking, you have to know, you have to be conscious on the error you are producing in your estimates. So if your final intent is to give data about intermittency, for example, to policymakers, maybe the error cannot be, we expect that error are not accepted in a large fraction. So the point is always considering the final use, being able to carefully share and spread the results of our approach. Or if you need some particularly fine-tuned data, actually they should be constructed together with the final intent, actually.
Thank you, Isabelle. We'll move on to Simone Bizzi's presentation. Simone, can you share your screen,
Good afternoon.
please?
Today, I'm going to, so first of all, my name is Simone Bizzi. I'm an associate professor at the Department of Geoscience, University of Padua. And we have been working on satellite data set to monitor river dynamics a lot over the last especially 5-6 years. So my presentation will be a little bit an overview of work that has been done by many persons, but you will see also some reference to publication if you want to have more information. And the first things I care when I start this type of presentation is to provide an idea of why, at least in the work I'm going to show you, what we want to understand looking at satellite data. So as a fluvial geomorphology, we are interested in understanding river trajectory. Now, what you see here on the left is a common geomorphological trajectory that many rivers in Italy, especially center and north, experienced in the second half of the 20th centuries. So they were braided, transitional, wandering, and they simplify in size and narrowed. It's a common process that occurs in France a lot too, especially in the Rhone Basin. For instance, Hervé Pieguet, Barbara Belletti, and many others worked a lot on this. So if you want to understand this kind of river trajectory that obviously are proxy of the sediment transport that are occurring, erosion and deposition process that are happening, sediment supply and so on, you need to identify what is commonly referred in literature as the active channel. So it means the part of the channel that is regularly reworked where sediment transport occur, and so vegetation is not growing on a windows of 1-2 years. So a regular flood, early flood, is able to flush away the vegetation and to initiate sediment transport and so rearrange sediment. We know that this active channel width, but also the active channel dynamics in general, tells a lot about what is the river trajectory. And in order to be able to monitor this type of trajectory, traditionally we look at historical orthophoto and we manually map the active channel, as you can see here for the Trebbia River and Po River from 1954, 1998 to 2020. You see how this river change over time. But here we are speaking about decades. So we had only one orthophoto, so one shot in time, normally in spring in low flow period. And you have one photograph in time every, in the past, 70, 80s, normally 10, 15 years. Now, more regularly, every 3-5 years, you have a picture. And thanks to this, we have been able to understand a lot about how the river behave in the recent past, and then how likely they are going to behave in the next future. But nowadays, thanks to the satellite, you can also think, can I automatize this task? Can I identify water channel and sediment bar and map the active channel mask automatically? Because if I have to do it manually, it requires a lot of time. You can do on few river, very unlikely you can do for many dates a national scale, for instance, or a global scale, for instance. This is something cannot be done. So since satellite data are more and more common, let's try to do it with satellite data. Here you have a number of limitations. There have been some very nice work in literature. One is from Greenberg or from Vamsi. Here you have a citation where they've been analyzing the Landsat, so the last 40 years for large river globally, and they were looking at how planimetrically the river was eroding new area and abandoning the old area of the active channel, and then they were able to understand how fast they were moving, how much quickly they were able to rework a floodplain area, and so on. And so these work are really very nice example of what we can do nowadays with Landsat. But this is working only on large river, and all this work only were mapping water. Now, if you could have water almost every day, clouds would not be a limitation. Mapping only water and having the period of high flow mapped in would be a very good way to map the active channel. But on average, you have, depending on where you are, 2 images without clouds, or even 1 per month, sometimes none per month, and very unlikely this is during period of high flow. So if you map only water, you risk to miss some part of the information, and how much information we were losing is something somehow unknown so far, because we were not able to do better than this. In 2024, with Patrice Carbonneau, we published this paper where we propose a classifier that we apply a global scale that, as you can see here on the right, is able to map not only water in general, but is able to discern river water that you can see here in light blue in this first column from lake water that is green. So you are able to discern lotic and lentic. This is because it's not a pixel-based approach, it's a deep learning where also the shape of the object is somehow entering into the classifier ability for discerning different type of water. And then where you have light blue, we add river sediment that are the red spot that you see, for instance, here in C. So basically we are able to map river water, lake water, and sediment bar at the global scale. Then a question that also the previous colleague was underlying, stressing, and it's when I have lesson is one of the most important things I try to teach students. Nowadays it's super easy to generate a classification. All the work is about to understand how good is that classification, the accuracy and certainty, when it works and when it doesn't work. If a classifier is perfect, you can throw it away, probably it's useless because it's impossible. So this is an important thing when you see works done with satellite. Now here there is no time to go too much in detail, but in the paper you can find all the information about the accuracy. Once we have been able to automatically identify river water, separating it from background and lake water, and including sediment bar, we said, okay, we classify these every month, because more or less you can have an image every month, especially in Europe. And every month we classify the active channel. And then in 1 year, you can create an envelope of all the monthly classification, and this could be a first estimation of an active channel. To give you more concrete example, what you see here is the River Po in Italy, one of the largest river in Italy. And here you see different type of orthophoto. The white one is the traditional orthophoto done manually, man-made. And then here you have yellow, threshold 1, violet, threshold 6, red, threshold 11, where you go more, let's say, threshold 1 means if a pixel is classified at least in 1 month as river water or sediment, I will keep it within the active channel. A threshold 6 means that a pixel must be classified as river water or sediment, river sediment, at least 6 times. So it's more conservative. But in this way, you reduce classification error. Maybe that month you classify it for a limitation of the classifier and so on. So in this way, you are exploiting the richness of the monthly classification to generate various types of active channel mask. Again, if you want, all the detail can be found in this paper that was recently published. Once you have the active channel, we have done an additional step, and then you can look like every year the active channel change position. I forgot maybe to say an important thing. This model that you see here are working with Sentinel-2 data. So there are 10-meter resolution in the visible and near infrared. And most of our work, we analyze the whole historical archive or Sentinel-2, so means from 2017 to 2025. So you start to have 8 years of data. That is not so bad. But obviously, you cannot go back 40 years. But you have 10-meter resolution. Let's say, it depends on what you want to do. For these 8 years, now, every year, we can map the active channel and we can map how it is changing over time. So what you see here in blue in this different picture and in violet are violet age of disactivation. Deactivation means area that were active channel 1 year ago, 2 years ago, or 7 years ago. Whereas what you see in blue are area conquered by the river. So area that was not active channel 1 year ago, 2 years ago, 7 years ago, and it is now active channel. So we can automatically map where the river is going. And obviously what you see in this graph here with this bar plot, the blue is activation, the violet is deactivation, and here are reach. Reach are 2, 3, 4 kilometer river length, geomorphologically homogeneous, along the river Po. So we are speaking from Turin to the Po Delta. So this is around 450 kilometers, where we have active channel every year, and we automatically, if you do it manually, this would be a work of months, super tedious. And you have also, you can map the net. So if the active channel is widening or it is narrowing. Interestingly, we also found a nice correlation between what we can call a proxy of river morphology. For those who has more knowledge of fluvial geomorphology, also a proxy of the braided index. That is what we can call the ratio between sediment and water. So if a pixel were classified mostly as sediment or mostly as water, you have a ratio. Higher it is, more multi-channel is the river. And there is a very nice relationship between this index that we calculate automatically from the satellite and the area of activation and deactivation. So basically, using this satellite data, we can characterize the river type, and we can also predict how much dynamic in terms of activation and deactivation will be, obviously with some uncertainty. The interesting part, there is no time to go too much in detail, but if you look at the confinement, this is artificial confinement, and it's telling us, if you see reddish color here, so more is artificially confined the river, less is moving, and this is pretty well known. And normally also more simplified is the river morphology, so sediment water ratio is low. And here we have also, in the last lower bottom here, we are also having this relationship year by year, where obviously you have a direct link between the degree severity of lateral dynamics and the discharge volume. Higher is the discharge volume and more dynamism you have. This is intuitive, but the beauty of this approach is that you can quantify it for different reach along a very large river. We are also working, this paper is published, so if you want to have more detail, you can find it here. Instead, this work is not published, but just provide you an idea of what you can do with this type of classification. You can start to look also at channel processes. So if you look at the pixel history, so for instance, here, if you look at from the 1st of January 2019 to the end of 2020, 2 years, you can look if a river was mostly water and became sediment, or the opposite, was mostly sediment and became water, or was sediment and was vegetated, colonized by vegetation, and so on. So if you play with the pixel history and you play with a number of criteria, remember you have a pixel information every month, you can map process such as water bank retreat, bar erosion, vegetation disappearance, sediment bar appearance, and vegetation encroachment. So you can also start to have a kind of history of the process that are occurring in this area. This is an example. What you see here is a GIF of our method. So what you see in black is the envelope of active channel over 8 years analyzed. And what you see, this is the Tagliamento River, so a multi-channel river. And what you see in color are water channel frequency year by year. And so it's just an example of an animation that is just with the purpose to show you the richness of the information that this type of classification and the satellite data that we have embed. But very often the real problem is not the availability of information, but our ability to exploit, to analyze, generating from information knowledge. This is difficult and require also very good data analysis skill. In the past, a geoscientist was mostly a descriptive science. Now is more and more data-driven, which is good, but is also dangerous. So this is something you as a student, you must think about the fact that you need more skill in data analysis, but you also need always to validate this data with more field evidence as possible. The main limitation of everything I have shown you is that is based on Sentinel-2. And so we can go back only of 8 years. Now we are working, actually we are almost done with this. We are extending the same approach you have seen so far with Landsat. And the main game here is again a little bit of deep learning, because we don't classify the Landsat, but we create a fake Sentinel-2 from Landsat, and this is an example of fake Sentinel-2 that you see in this image, and then we apply our algorithm on the fake Sentinel-2. Again, another of... We are applying this monitoring, let's say, this approach at national scale in Italy, and we have also a little bit of collaboration just starting with Hervé Piéguet and Barbara Belletti to start to test these procedures also in France. And this is an example of the web tool we are developing to exploit, but also to give to end user this type of information. So it's not remaining only in the science domain, but can be used for river management. And I just want to, just a couple of slides to say two things. The first one is obviously I have short time. I have to give you an idea of what we are doing. This type of work is very time consuming. So even make operational and assess the uncertainty and the feasibility of this chain of analysis is very time and resource consuming. And especially if we want to go global, apply being able to compare the same classification in different parts of the world, we need common standard and we need common data set for validation. This is common data set for validation that are common procedure in other discipline. For instance, for river mapping are not yet there. And this is something is really an important needs for the future, so that different classifier can be tested over the same validation data set that is wide enough, global or national or continental. One thing to mention, we are also working a lot with sediment network, network scale sediment transport model. So model that simulate how much sediment is transported in every reach of a river network, where the sediment is coming from, the type of grain size, sediment fluxes, and so on. And why I'm mentioning it? Because understanding how sediment are transported in a river network is very important. And in the past, it has been done too much decoupled from the study of morphological change. So there are people studying how much sediment is transported to a river, other that study how river change over time, but the two things do not speak each other. And instead, in the future, this is exactly where we should go. Now we can map morphological change more and more widely, slowly, and then we can also model sediment flux. We can collect sediment transport data, and these two information, these two evidence, morphological change and sediment transport information, must speak each other more and more. This is the only way, then, when you build this evidence, you can understand what it has been, the river trajectory in the past, and you can foresee the future one under future water and sediment fluxes in this climate change period. And I just want to finish saying that for a student, you cannot know this, and it's an important point. This is something that is already feasible. The data is already there to do this. Why it is not happening so fast, or why it has not yet been happening, is mostly for resource and time limitation. But in order to go in this direction, we have almost most of what we needed. We just need to do more research in this direction. That's it.
I have a question, Simone, concerning the role of AI, which is now used in river geomorphology studies, where you did mention the fact that it takes a lot of time, this type of work, but do we save time thanks to AI? I mean, do you think AI, in your opinion, is it going to be more, is AI likely to dominate, to basically be the key tool in the river science, or will there be limitations and we will need other additional techniques?
No, thank you for the question. This is artificial intelligence is radically transforming many science, and river science is not an exception. Is happening. A couple of comments from my side is that first, this is many other people, but I don't like so much the word artificial intelligence. I prefer deep machine learning, because it's not necessarily so intelligent. It's just very computationally intense. For sure is an opportunity. For sure we need to use it. But we need always to, for instance, artificial intelligence or deep neural network model provide a nice output or nice result, but you don't know why. So we don't know what is the criteria that the classifier or the model is using to predict the river. For instance, now we are working on modeling that are using the past pixel trajectory to predict the future one. Let's say this is going to work, but we don't know why. And instead, the why is fundamental in science. So there is an important branch of artificial intelligence that is only to create a model that is trying to understand how your artificial model works. In other words, what are the criteria that the model is using? All of this maybe was a bit confused, but to say it's an opportunity, but it's not all the story. is only powerful up to a point and must be integrated with knowledge and testing of our hypothesis of how the system works in terms of equation, in terms of understanding. This is unavoidable, otherwise can be really dangerous, really, really dangerous. Yes.
D'accord, merci beaucoup.
Thank you, Simone, for your presentation. With this interesting information, I do have a question, curiosity. You talked about you did not use Landsat images. You created a fake Sentinel-2, and then you applied this to deep machine learning. So how were you able to achieve a fake Sentinel-2, and what approach? What approach did you use to get to this? So
maybe if you can translate the second part. The first part, I'm okay. If you can just translate the final part of the question, please.
Yeah, the final part was more about the machine learning that you're going to apply in the fake Sentinel-2. Will it be a pixel-based machine learning, or you're going to based on other parameters to apply your machine learning?
Okay. Thank you, Gloria, for this question. And so the reason why we decided to create a fake Sentinel-2, a fake Sentinel-2 from Landsat, is because the training of our algorithm require 1 year of work and a huge amount of data that then was in different period updated and fine-tuned. So to create a new model was a huge work, first. And second, we wanted to have a model that could analyze Sentinel-2 and Landsat together. So you need to harmonize these two data sets anyway. And when you are looking at river trajectory, so how active channel change over time, of course you are looking for accuracy, but what is more important for this type of analysis is consistency through time. So even if the model has 20% of error, but the error is always the same from your first period to your last period, that is an advantage, that the trajectory increasing or decreasing is consistent. And so this is the reason why we said we are going to use the same model and we are going to build a fake Sentinel-2 for this reason. And instead, the second part of the question is, no, our model is not pixel-based, is a CNN, so it's a convolutional neural network based on a specific windows of analysis. So it is able to use property relate with shape. But here I'm general intentionally, because it's part of the answer I said before. For sure, the model is somehow looking at some property of shape, but which property of shape is a little bit unknown, because you have to interrogate the model in order to understand it. And obviously is related to the data set that you have used for training. But definitely it's also understanding how pixels are organized in a specific different windows of analysis. And then you also have some attribute of shape in the ability of the classifier.
Thank you, Simone. Well, then we'll close